Now, after completing our first unit, we will study the actual components which are used in electronic devices. Starting with the simple device, we will move forward to complex ones. This unit is all about PN junction diode. You are familiar with P-type semiconductor as well as N-type semiconductor. PN junction, as the name signifies, is a junction one side of which is a P-type semiconductor and the other side is N-type semiconductor. However, it does not mean that if you bring a P-type crystal and N-type crystal and place them one after another, then it will become PN junction. Neither sticking them with one another will make a PN junction. It is a whole process which is carried out completely in factories where diodes are being manufactured. You will not be able to construct it at home. The principle and process behind construction of semiconductors requires not only a separate chapter but a separate subject. Processes like etching, crystal growth, lithography, all these are taught in VLSI technology or advanced electronics. Here, we will not go in much depth. You simply assume that the entire semiconductor crystal is of the same semiconductor material. And also, in one side of the semiconductor, P-type impurities are injected and in the other region, N-type impurities are injected. This is called metallurgical junction. At the junction, few more phenomena will also occur and we will be focusing on these phenomena in the whole chapter. Otherwise, portion which is quite far from the junction can be treated as normal P-type and N-type semiconductor. In the P-type region, we have a huge number of holes and in the N-type region, we have a huge number of electrons. This difference in charge carrier concentration will lead to diffusion current. Electrons will be moving from right to left, whereas holes will move from left to right. Both will result in diffusion current in the left to right direction. But as soon as the charge carriers will move, another phenomena will emerge to take place. Like after a while, when the charge carriers are transferred to either side, the dopant atoms will get ionized. These immobile charge carrying dopant atoms will create an electric field. And we know the direction of the electric field is a direction in which a positive charge will move if it is kept freely. Now, assume that we have kept a positive charge here. Both the ionized acceptor and donor atoms will force this positive charge to move from right to left. So, we can say the direction of the electric field will be from right to left. So, you can see that this electric field will result into a drift current and the direction of this drift current is opposite to the direction of diffusion current. So, one thing should be clear to you that the charge carriers will not move infinitely. They will move until they reach equilibrium, and in equilibrium the drift current will be equal to diffusion current. Diffusion current remains comparatively constant. However, drift current will increase as the number of ionized dopant atoms increases. When the drift current is equal to diffusion current, no further transfer of charge carriers from either side takes place, and the phenomena of equilibrium limits the length of ionized dopant region. The region in either side of the metallurgical junction in P-type and N-type semiconductor, which is depleted of charge carriers, is given various names like depletion region, transition region, and space charge region. This depletion region is characterized by uncovered or ionized dopant atoms, and here also the type of equilibrium which is taking place is dynamic equilibrium. The length of this depletion region is referred as depletion width. So remember that diode and PN junction are same thing. Depletion region, transition region, and space charge region are same thing. Uncovered dopants, uncompensated dopants, or ionized dopants mean the same thing.